Welcome to CW 1.7. Today we're going to be reviewing what you learned in Algebra 2 as far as graphing polynomial functions. So to start off, right here are two examples of polynomial functions. A couple defining characteristics is you'll notice that the exponents are whole numbers. And also, you can have fractions, but there are going to be no variables in denominators. So again, fractions are okay as long as there aren't any variables there. And then when we go to non-polynomial functions on the right, you're going to see that here. So I'll highlight what's wrong here. You see right here the root. The root can be thought of as x to the 1/2. 1/2 is not a whole number. And right here we can see that there's a variable in your denominator. Or for those of you who remember exponents, that's x to the -2. And again, that is not a whole number. Whole numbers are going to be 0, 1, 2, 3, ... That's a quick refresher on what it means to be a polynomial function. The first thing we got to do is talk about the leading coefficient. Now, in my class, we're going to refer to it as leading term. So if you remember my Algebra 2B class, if you're in it, I often call it LT. So LT is in the term at the very front. So in this one, I can see that it's x cubed. This one's pretty easy. I can see it's x to the 4th. And notice how these are written in order. So it's the term at the front when it's in order. And this one, a little bit tricky. It's not simplified. So imagine you multiply this out. I have a -4x cubed here. This will produce an x squared, and this will produce an x. So multiply that together, and we're going to get -4x to the 6th power. So there's our leading terms. Now the leading term is significant because you use that to find what's called end behavior. So end behavior, I made a chart right here. You can pause really quick if you want to just copy this chart down. Whenever we have a leading term, we have it in the form of ax to the n. This chart is going to represent every possibility. So if a is positive, that's what that means. A is positive. This means a is negative, meaning greater or less than 0. But n is even. That's like saying x squared. So imagine a positive x squared graph in your head. On the left and right, both arrows would be going up, or think of it as up, up. If it's a negative x squared, flip that in your mind. Now you're going down, down. If it's odd, imagine x cubed in your head. That should look something like that. We're going to go down and up. And if it's negative x cubed, simply flip that to get up and down. So that's a complete end behavior chart, and that should feel pretty familiar from your Algebra 2 class. So we're going to use that here. That's positive x cubed. You can look at your chart or just think about it. Down, up. Positive x to the 4th. That's going to be up, up. -4x to the 6th. That's going to be down and down. And there we have it. Now we're going to actually graph these. So it says find all zeros. We're just going to do everything. We're going to find the zeros and also graph it. So we'll start there. Zeros, recall, that just means x-intercept. So let's solve that. 0 equals x cubed plus 3x squared minus x minus 3. This is a group factoring question. So remember that, look at the first two, look at the last two and factor. X squared, x plus 3, take the -1 out, x plus 3. So now we have x plus 3, x squared minus 1. And I want you to factor it all the way. So make sure this is factored as far as possible. This is what we want. From here I can see the zeros are -3, -1, and 1. Now this m is going to stand for multiplicity. So hopefully you recall that from your last class. The multiplicity is simply referring to the exponent on each of the zeros. So if I look at where the -3 came from, right here, notice how the exponent is 1. And for all of them, the exponent is 1, which actually means we're just going to write 1 under all of them. And then hopefully you recall, if it's odd, that means these all cross. So I can write C. So if you've forgotten what that means, just remember for multiplicity, even is one scenario, odd is the other. If it's even, we say touch. Odd, we say cross. If you want to see an example of it, touch means like a parabola, like it just touches the axis like that. And then cross means it goes through like that. Okay, so there's our zeros, multiplicity. And then all we need is our leading term and end behavior. The leading term I can see is x cubed, which means end behavior is down, then up. Now, one more thing that's helpful is to have the y-intercept. That will help us graph. And I can see that's right here. That's -3, so that's not too bad. Now let's graph it. The key is where to start. Always, always start with the end behavior. So I'll put a down arrow here, up arrow here. Again, always start end behavior. Make sure you write that down. This right here is where you start. From there, you can go a number of ways. I like to do the zeros and basically the intercepts. So -3, -1, 1, and -3, and just draw it. It's going to cross through each zero. So cross, cross, then cross. We have an iPad, so let's just move that right there to make it nice. And there's our graph. We're done. Okay, let's do a little harder example. Same thing, we're going to start by finding the zeros. So 0 is equal to, let's take out -x². That's x² minus 4x plus 4. So now I have -x² times x minus 2 squared. So the zeros are clearly going to be 0 and 2. My y-intercept, and I can plug in 0 here. I can see everything becomes 0. So let's write 0. The multiplicity, notice how both the exponents are 2, which means these got to be 2. So I'm just lining it up. So 0 is 2 because of this one. 2 is 2 because of this one right here. Your leading term is -x to the 4th. I can see that right here, which means our end behavior is down and down. So to sketch it, again, where do you start? End behavior. I'm going to put down, down. Let's mark the zeros, 0 and 2. And now we just put it together. Notice the y-intercept is also 0, so that's handy. These are both 2 for the multiplicity, which means they're both going to touch. That's important. So as I'm approaching 0, it's going to bounce or touch. Approach 2, I'm going to bounce again. And I'm going to move that to make it a little nicer right there. And there's our graph. Okay, so that's it for the review part for today. This is going to be new for all of you. Using the intermediate value theorem. When you guys take calculus next year, they'll call this IVT, so short for intermediate value theorem. So I'm going to show you what, in a nutshell, it means. It says, show that the function x³ minus 2x minus 5 has a real 0 between 2 and 3. So 2 and 3, these are the x values. So it's saying x equals 2, x equals 3. So if I'm drawing the situation, it's saying imagine your graph. Here's 2, here's 3. We're saying if we zoom in, there should be a 0 somewhere in there. It should happen. So I'll show you how to do this. We're going to first find f of 2. So f of 2, you plug that in, that's 8 minus 4 minus 5, so that would be negative 1. So f of 2 is negative 1. So if I go back to my graph, we're basically saying there's a point at 2, negative 1. So here's 1 point. Now we're going to plug in 3. F of 3, that'd be 27 minus 6 minus 5. So f of 3 must be 16. So 16 is like somewhere pretty high up. We're going to say it's like up here somewhere. 1 dot. What we're saying is we're trying to show that there's a real 0 that happens in this region here. So you can imagine a dotted line right here between 2 and 3. Now intuitively we understand there must be a 0 here because we know the dots have to connect. So no matter how I draw this thing, I have to cross through the axis at some point, somewhere, if I'm going to connect those two dots. Because we know for it to be a polynomial function, all the dots are going to connect in some way. So how to write that mathematically? This is what we're going to do. We're going to say f of 2 is less than 0, and f of 3 is greater than 0. So f of 2 is this negative number, f of 3 is this positive number. So I'm going to put comma. Therefore, there exists some value, a, to make that more clear, a, between 2 and 3, the x values we were working with, such that f of a is equal to 0. And that's how we're going to formally state our answer. That's it.